Hello. Today we're going to be talking about compound inequalities. And compound inequalities are going to use two different words, the word and the word or. And so I kind of want to talk to you about what the definitions of those words imply. So when you see the word and in a sentence, that word means that both parts of that statement must be true. So in that red example here, we have Ricky, who is a blonde and over 6 feet tall. So you can picture Ricky, who is a 6+ foot tall human and is also blonde. Okay, it has to be true for both. When it's the word or, it only means one part of the statement has to be accurate. So when we say Ricky is a blonde or over 6 feet tall, well, Ricky could be 6 feet tall, Ricky could be a blonde, or maybe both. Okay, so that's what those words mean, and that's what we're going to use when we see these things in mathematical statements as well. So on the next page I have some examples, and we've been asked to solve. So these are two inequalities that have been put together, and we want to figure out what values of x would be true in part 1 for both x plus 7 less than 5 and 2x is greater than negative 12. It has to be true for both things. So what we're going to do is simply solve both of these inequalities. So x plus 7 is less than 5. If I take that, I'm going to subtract 7 on both sides by the subtraction property, and x is less than negative 2. And if I solve the other one, I'm going to divide both sides by 2. X is greater than negative 6. So to illustrate this, we graph it on a number line to show all the possible x's. We need all the x's that are less than negative 2 and all the x's that are greater than negative 6. Now my x's can't be negative 2, it's just less than, so we put an open circle. Same with negative 6. They can't be negative 6, they're just simply greater than. Now all the numbers less than negative 2, such as negative 3, negative 4, negative 5, and so on, are to the left. So we would shade this way. All the numbers bigger than negative 6, negative 5, negative 4, negative 3, and so on, come above or greater than the negative 6. So we would shade to the right. And so we want where it's true for both. Well, these numbers that I have x'd out, those are the numbers that would apply to both statements. Okay, and so I can pick any of these numbers, negative 5, negative 4, negative 3, or really any number. I could pick negative 4.5 if I wanted. I actually could pick a negative pi if I wanted, and plug those in for x, and both of those statements would be true. We can try it. Let's try negative 4. It'll be easy. If I do negative 4 plus 7, is that less than 5? Well, we get 3 is less than 5. True. If I put 2 times negative 4, is that greater than negative 12? Well, that's negative 8, which is indeed bigger than negative 12. True. Okay, so negative 4 would work for both, and thus the and. Let's move to the second problem. If you notice that we're kind of put together into one compound inequality here, so we don't have the word and or here, but this has an assumed and. We're supposed to assume that negative 5 is less than 6x plus 7 and 6x plus 7 is less than 31. But of course, this is a much more succinct way of writing it over here on that left side. So if we solved over here on the right where I wrote in green, I'm going to start by subtracting 7 on both sides, and negative 12 is less than 6x. Then divide both sides by 6, so negative 2 is less than x. On the right I'll do the same, subtract by 7. And then divide by 6. So x is less than 4. So we want to make sure that this is true for both, that the x's are bigger than negative 2 and smaller than 4. So we have an open circle at negative 2 and an open circle at 4 because Again, not equal to, just less thans. X is bigger than negative 2, like these. And then x is smaller than 4, or things like this. And so it's where we made those x's, and it's there in the middle of them. Now, if you notice what we did, I could solve the original problem as it stands, but when I subtract 7, much like I had to subtract 7 from the 31 and from the negative 5, I have to subtract 7 on both sides. And we end up with, well, negative 5 minus 7 is negative 12, less than 6x, which is less than 24. And then in both of cases, I divided by 6, so when I divide by 6, I divide it by all three parts again. So negative 2 is less than x, which is less than 4. And that is exactly what we graphed. Let's try one more. Here we have two inequalities, but the word or is sitting between them now instead. So we'll still solve each of them individually. 3x minus 3 is less than negative 9. Well, we'll still start by adding 3. So 3x is less than negative 6. And then when we divide negative 3, or just going to divide regular 3, x is less than negative 2. Or, well, over here I just have to divide by 7 to get x alone. So x would be greater than 4. So what does this mean? Well, this tells us that we want some value for x that would be either less than negative 2 or bigger than 4. So we can graph all the options that would work here. So if we're less than negative 2, well, I still have an open circle at negative 2, and all the x's less than that are shaded off to the left over there. And if I want all the x's bigger than 4, well, we have an open circle at 4, we shade all the possibilities bigger than that. And so because it's an or, it's really just a matter of where could it be true? It has to be one or the other. So if I were to pick, say, negative 10 for x, well, negative 10 is less than negative 2, so it works right away. I don't even have to test the other one. If it works, great. If not, who cares? Because it works for one, so it works for the whole inequality. And that's the idea of compound inequalities. We are done.